Good morning, friends. In this video, we're going to look at Green's theorem, and this theorem connects line integrals and double integrals, and it essentially simplifies calculations to give us insight into fields and regions. So what does that mean? So I have here the theorem, and it provides a relationship between the circulation of a vector field along a closed curve and the behavior of a field inside that curve. So this is the formula for Green's theorem that shows that relationship. And so to break it down, C is a closed curve that forms the boundary of a region D, and D is a region closed by C. P, xy, and qxy are the components of a vector field. Okay, so next we're going to look at the key conditions that we need to meet in order to apply Green's theorem, starting with the curve C must be closed, and so it forms a complete loop with no breaks. For the second one, it has to have a counterclockwise orientation. The curve must be oriented in this way, and if it's clockwise, the result will have a negative sign. So third condition, smoother piecewise smooth curve, which means that the curve should be smooth or consist of smooth segments. And lastly, vector field continuity. The vector field F must have continuous partial derivatives inside the region D. So that's what that means. And so a way to think of Green's theorem is as a way to trade a line integral around the boundary of a region for a double integral over the area of the region. So instead of summing the effects of a vector field along the boundary, we calculate how the field itself behaves inside the region. So for example, the term measures the rotation or curl of the field inside the region. And the theorem essentially says the circulation along the boundary equals the total curl inside. So here's how Green's theorem simplifies problems. Instead of computing a potentially complex line integral, we switched to a double integral. So we're going to look at a few examples in a second, but also special notes on orientation. Counterclockwise. When you have it counterclockwise, the result of the integral is positive, and if you have it clockwise, the result will be negative. So it's important to pay attention to the direction to avoid sign errors. Okay, so let's look at a few examples, starting with this given graph here. Zero, 1, 1, 1, 1, 0, 0, 0. Here you can see that it's closed and it is going in the positive direction, so we are able to apply Green's theorem. the area enclosed here, it's our area D, and we're also given this. So we have our P and our Q. From there, we're able to apply our formula. So this formula evaluating from 0 to 1 and from again 0 to 1. Oops. Go ahead and integrate that. To 1/2. Okay, so let's try another. Here we're given this graph. We're going to practice setting it up. So yes, it is enclosed and going the counterclockwise direction. So we can apply our formula. And we see here that y runs from zero to y is equal to x, and x runs from 0 to 1. So you can go ahead and plug those in. Okay, so that's how you would set that one up. Let's do one more example for Green's theorem. For this one, we're given this graph, y equals x squared. We have this point 1, 1, 0, 0. 0, 1. We got our enclosed space here moving in the counterclockwise direction. Okay, so go to graph y equals x squared. so now we can apply our formula given that. For our y component, we are evaluating from here to here. So this is x squared, and this is 1. And that's what you get as your answer for that one. Okay, so here is a visual representation of Green's theorem. The red curve represents the closed boundary C, which is a circle with radius 2. The shaded red region is the domain D enclosed by C. And the blue arrows represent an example vector field F with components P, x, y is equal to negative y, and Q, x, y is equal to x. And the arrow along the curve indicates the counterclockwise orientation, which is required for applying Green's theorem. So, to summarize that, the visual shows how Green's theorem connects. Visual shows how Green's connects 1, the line integral of the vector field F along the boundary C, along the curve, and 2 connects to the double integral of the curl over the region D. Okay, so that's it for this video in Green's theorem, and I'll see you in the next with Stokes' theorem. So, bye friends.